digital twins. I mean, there's digital twins, or twins are an important subject of study in medicine as well, because it's the question whether something can be a digital twin even before it comes into physical reality. If we compare across different twins, then I think there's a lot to be learned, and maybe the most important aspects for digital twinning, in my mind, is this front-loading aspect, to learn from the behavior of the buildings later on that we do not understand in its entirety, and to take them into the early stages of design. This probably also guesses to you that my background is architecture. I'm lecturing at the RWTH University in Aachen, at the design computation group, which I have the pleasure to head. We are also organized in a BIM center Aachen, together with colleagues from civil engineering and from machine building and manufacturing, to bring together different competencies from our various domains. More of that later on, and a few examples. And of course, I also have a digital twin, at least one in the US, because I didn't delete my Facebook account yet. Even if I do, it's probably living into eternity. And the other, I have been enough in China to probably also have their digital twin. Which also is something that we probably have to discuss later on, because so much of what is going on during the operation phase in our buildings, of course, pertains to people who are using the products that we build, both in infrastructure and in buildings. So Yannis tasked me with giving a presentation about the potential futures of digital twin standards. And to most people in the room, standards might not be the most attractive topic. I dedicated quite some time per week to standardization, and there's enough bad mouthing about standards that I thought I'll start off with an article earlier this year in the New York Times that was talking about this joy of standards, because it's really imagine what would happen without standards. Imagine, for example, and this is actually what the author Andrew Russell started with. Imagine the building industry would reinvent the dimensions of bricks every time they would start building. So that's why having these standards, even though they're laborious to adhere to, and they're often very complex, is quite important. Another example that has been shown in a study cited below from quite some time ago is that in each one of your machines there's approximately 250 standards just to make a laptop work, and quite a big portion of that is not entirely driven by industry, but is also driven by standardization organizations, standardization bodies, such as in our domain, for example, Building Smart, which I and Andre and many others, and Gang, many others in the room actually dedicate a lot of our time from academia to bring our insights there. A lot of these standards, in order to make your laptop work, and in order to make digital twins work, we've got to make sure that we can use most of this in a fair way, and that we can actually have access to this, and that the whole market that is going to eventually evolve around digital twin is going to have access to this. So this just to set the stage. At the end of my talk, I will also give a few of my answers to the question that has been set out by Yannis and his team. But let me first start off with the future of digital twin standards. In my view, is decentralized, open, heterogeneous, and interlinked. These are the very well known evolutions of building information modeling. And I really think that introducing that the more information we make available, the less feasible centralized solutions are, and the more we have to think about how to decentralize them, how to superimpose different sets of information, like in the 7-set Venn diagram here, in order to get what we want to achieve. And here again, touching upon, or in the continuation also of Andre's talk, it's very important to think about what we actually want from these digital twins, and what it is that we want to achieve. This is a very short overview of what I'm going to briefly touch upon with some examples of all these topics that have been framed in a slightly different way throughout the morning and throughout the presentations tomorrow. And behind many of them, of course, we have a lot of these 3-letter acronyms and 5-digit numbers, which by standardization organizations, which I think belong within the realm of digital twins and and have some potential to allow us in the building industry to design the digital twins that we have in mind for our different use cases. But before we actually do this, let's take a look at the relation to, and we have touched upon this sometimes earlier, between the relation between building information models and the digital twin itself. So let's turn to ISO 19650 and to the good old wedge. And it seems after the presentation of the earlier this morning that the wedge on the right hand side is going to be continued by the digital twin. So once we come once we have designed everything in an integrated way, and we're actually talking about services, we can actually go into this life cycle management stage, and we can start have our physical assets also communicate with these services and integrated information in the form of a digital twin. To put it into another perspective, while the so-called residual project information up here is up here. Do we have a pointers somewhere? Use the mouse, and I have to turn away from you. These residual project information. This is kind of the static. This is the static part of what has been left behind from the planning stages, and all these event-driven operation in the asset operational phase, where we're talking about in this context of the 19650 is actually. It actually pertains to the digital twin in my case. But let's start early on, because as particularly in Europe, 75% of everything that we in the building industry are going to do in the next couple of years is actually in existing buildings. So the case that we're starting from scratch, that we're starting with an entirely new building and we can plan a digital twin from the get-go, is actually the exception to the general rule that we have to actually digitalize what we find. And this is touching upon the acquisition. This is touching about the earlier topics that we have been talking about earlier, and that Jannis showed in this presentation. And there too, we have a couple of useful standards that we might want to use and that we might want to employ if we want to do large-scale scanning, if we want to do large-scale scan to BIM, if we want to scan on a regular basis, if we want to do this every year, if we want to do this for our cultural heritage assets or for our brittle infrastructure, if we want to do this in a continuous way and we want to see the differences, strongly depending on what it is that we actually want to do. We have these wonderful standards given to us by the computer graphics community in the case of E75 and HDF5, the hierarchical data format, in its 5th revision, in order to capture very efficiently these large data sets from billions of points. And why? And the other thing that I think the community, the building and construction community, really desperately needs is to come up with standard reference data sets, because up to now everybody has their case study and they're keeping it to themselves. And in order to make and in order to actually profit from this, we in building and construction should start doing what the automotive industry and from this from the presentation earlier, what the computer vision people do. Everybody has seen the image on the left-hand side, right? This is you training. This is you training Google, creating Google training data sets on a massive scale to come up with reference data sets for object recognition for autonomously driving cars. When we want to efficiently create, make scan to BIM or scan to digital twin something in the building industry, then we might want to look into creating similar things like that in order to make it easier to actually cluster and semantically enrich what are scanners or what are photos actually or other image-based acquisition methods can receive, and in order to create enough of these training data sets to make the acquisition of this much easier. And as one of the examples that we did a couple of years ago is to pack up these reference data sets and actually publish them online so that the whole community can reuse them, just like the automotive industry has their standard data sets to reference. It would be good if we could start collectively coming up with data sets like this. Everybody that seriously does BIM probably knows about the duplex model. Everybody knows what the duplex model is. Everybody knows in computer graphics what the Stanford bunny is, and maybe we need something like that to build up in the academic community on point cloud acquisition, in order to be able to do things to actually mark up and cluster things that we see. I think it's particularly difficult to do this with point clouds, and particularly difficult with all the different types of buildings that we have to auto-classify point cloud information. But maybe if we start with images and start to superimpose photos of what we of the models that we already have with photos that we already see, then we might come up with something that would help us help the acceleration of the creation of digital twins based on common standards within our domain. And an example of this, and this is one of the reasons why HDF5 and E75 as standards for capturing and superimposing point cloud data sets over models might be something interesting. I know that we have been discussing this earlier, whether it's useful to keep these kinds of data sets for a prolonged time. But if we want, I really do think that if we want to accelerate into that direction, then we should do something about this. Another topic that also has been touched upon earlier is the introduction of dynamic data. So understanding of the physical behavior of our buildings, measuring things, Internet of Things, IoT sensors, and the ability to actually create good models of our behavior. Because again, this is something that is not enough understood. So the building physics community, they suffer from a lack of actual trustworthy data sets to calibrate their simulation models. And that being a part, an essential part of digital twins, to be able to recalibrate your operating buildings or build structures is an essential part. So we should really invest more in standardizing how we capture this data, and how we couple this to simulation and training data. And this is from the BIM Center Aachen, from my colleague Jörg Blankenbach. They, for example, use this in dike structural health monitoring, where this is we're equipping large structures with a lot of sensors in order to make predictions of the structural integrity of big infrastructural monuments or of infrastructural structures. Is really important. And again, there's loads of different already existing standards, and we should really take a look at what other industry domains do. Here's an example. In this example, MQTT and some geo domain extension to MQTT are very viable standards in order to use to connect sensoring and to set up sensoring networks in our domain. The same thing for if we actually want to react, if we want to simulate in our digital twins what they're going to do and how we can improve the performance and the behavior of our physical assets, then we have to standardize the way that simulations are captured, that components, for example, in our mechanical devices are standardized with regard to what goes in and what goes out and how things are calculated. The International Energy Agency has come up with a standardized way to set up these to set up for all building physics simulations, to simulate how the different components are described, how they're set up, what the critical values are, and nobody has to reinvent this again. And we can use this off the shelf and implement this in widely used standard applications in the domain. These are just two examples from this domain. Let's go on to other standards that are very relevant, that I think are very relevant and still under construction. So here is, for example, the OpenCDE API, which is if we really want to make digital twins communicate. And actually integrate all this heterogeneous information, that we need some domain-specific means to actually communicate in a standardized way. So this is something that is under rapid development. We have members in the room who are doing this, and I'm coming back to this idea of representing different things, or the many different things that we need in digital twins to be represented in these sorts of containers. And the OpenCDE API is an attempt, or is the effort to standardize some of the access of the different components that play a role in BIM models and in digital twins. So, for example, in this example taken from the specification, in an operation phase, you want to add or you want to modify something. You want to query how your building is performing. Then OpenCDE devises the way to actually to get the right information, to get the right models, to get the right sensor, or to get the right data. And to make it interoperable between different vendors of these systems. I'm in my statements regarding what I think is needed and what I think we should develop in the digital twin movement. I'm also coming back to the necessity to have object-oriented extensions to this. So by now, this is just give me this part of a model, or please integrate this another part, a new asset into the containers. But my argument is that it would also be, especially if we're talking about sensor data or profiles, historic data of the digital twin, that we would need object-oriented extensions in order to make sense and in order to allow us to do this across different systems. Okay, and to come back to into this idea. So how do we have different on the very right hand side? How do we have different all the different aspects that we want to capture in digital twins, and how do we store them, and how do we capture them in a standardized way? I suggest to heavily lean on the linked data and semantic web community that have devised many different or many means and technologies to not only model domains, to not only logically model domains, but also to break out of individual interoperability silos that the many different systems in digital twins represent, with standards that have been that have widespread use, that have lots of tooling support, that are robust and reliable, and can probably most important of all, really scale up to the size that we need. So the ability to actually interconnect all the different data sources that we have is not only on the instance level, where we want to tap into different information and resources and combine them, but also, and this is really something to look forward when standardizing the structure of digital twins themselves, is to reuse as much as possible of the knowledge that has been modeled in other engineering domains. So, for example, why we should never again reinvent how measures and units are made. We should, because we can't explain to other domains that we're doing it differently because we're the construction industry. But instead, use what we find in the rich landscape of these ontologies and structured vocabularies to really connect all of this together. And I'm going to show you very soon. I'm going to show you some examples of how such interoperability questions for digital twins actually look like. So if we want to connect all this heterogeneous data from sensors or from other reports, from structural health monitoring and so forth, then one of the standards that is underway is the Information Container Document Delivery, ICDD, which we submitted the second part because I'm also working in this committee. We submitted the second part for review in this stage last Thursday, and the idea here is that you can park any heterogeneous, even proprietary data formats in a structured way and connect different items, such as a single sensor or such as different documents or photos or scans or whatever between the different formats in your file. And I'm going to show you several examples in a minute. So here is the overall structure. I think that the part one, where the general decomposition structure of this container is standardized, has a pretty good chance to be adopted very soon. Part two, I'm not so sure, because they are proposing semantic extensions to that ability. I'm going to skip this and come immediately to a structural health monitoring application of this. This is not research that I have been involved in. This is by Al-Hakam Hamdan and Matthias Bonduel from the linked data in architecture and construction, LDAC, as conference series that we have now 7 years in a row, looking at linked data in this. So this is a so-called ontology modeling structural health damage and modeling crack propagation and modeling different kinds of damages and assigning them to models that we already have. It doesn't matter whether they are point clouds or whether they are explicitly modeled hand models or whether they're just photos. This is a neutral way to describe damages, and it shows because that's the way it is implemented, and it shows how such a multi-model container, according to this ICDD standard, can be used to hook up very heterogeneous information into and evolve them over time in digital twin models. And also it demonstrates one of the core strengths of these linked data approaches, that modeling these things, publishing recommendations and putting them out in the open to be extended for other domains is really much easier than if you go through the let's say an ISO process, ISO standardization process. Other things that might be interesting when we're looking at who actually owns the data, which is quite important for evolving digital twins of buildings that will last longer than individual lifetimes or than lifetimes of a single owner, is this notion. So this is what Tim Berners-Lee, the inventor of the internet, is currently working on, is kind of alternative means to social media platforms where you are the owner of your information and not a big company, where the information is stored in your realm, or where you can also externalize them on a service, but the idea is you are the owner of your data, and you allow others to give others rights to read certain aspects of your data, and you're the one who determines the shape. So we have adapted this concept from Berners-Lee and Ruben Verborg and others that are working on this Solid platform for several years now, to building data, to store information in such data pods and large sets of information also. And because this is one of the examples how storing it this way, how storing it in standardized ways, for example, gives you the ability to query across large distributed and interconnected data sets. Another example from the added benefit of using linked data in a digital twin context is the SAREF ontology, which is a model of sensors, all kinds of sensors. Only a few of these sensors are relevant to building and construction, but the importance is that other industry domains can model their sensors and can model the things that they say in their means. And we all do it in the same language. And if we building people or bridge people or railway people decide that these are the things that are very particular to our domain, we just take this and we extend this as little as possible and integrate it. And here's an example. This is some 5-year-old research or 4-year-old research of our faculty building, and a story that has been equipped with 50 sensors in legacy systems, and we just represent them as linked data sets, and we publish them on an end node, and then we can do standardized queries without really having to know how they're internally organized. Because the only thing that we need to know is what the representation as linked data sets in this SAREF ontology is. Again, which has been adopted by other domains as well, and which goes to show how quickly evolving these standards can be, and which also goes to show how minimal the kinds of information probably is that you need. Another example is the semantic sensor network ontology, which is standardized by the W3C consortium in collaboration with OGC. It's not. This is an example where standards evolve not only within one organization, Building Smart or ISO or CEN, but where actually you can collaborate on these things, such things as sensor networks across groups, and where you can reconfigure. Actually, you can give this to students and reconfigure and create use cases of the use of such standardized ontologies, such standardized vocabularies in a digital twin example. Here's an example of a museum that has been contracted in order to, for example, have a certain humidity and certain temperature over time. And where the contractor, the provider of the building in a DBFMO contract would get less rent if the building didn't perform as expected. And which is also a very important part, I think, in the future of digital twins, that we make these things part of the contract, that we as the owners of buildings, for example, the owner of public buildings or the owner of commercial buildings, dictate how we want information to be delivered, that we dictate how we are going to measure this, and that we make very certain who's owning this actually. And then one last aspect, which I think is probably not very high up on the list, is its long-term preservation. Because if we actually want to learn something, if we actually want to optimize the performance of our building, then we have to have learning curves of not just this year or in 5 years or 10 years. We want to own the building. Somebody else is going to own this in 100 years. And if they want to do something, then the digital twin shouldn't be dead. So we have to make sure that we still can read and still can get provenance information from where particular information came from, and that we can still access it. And if you think this is an easy task, well, think twice. This is rocket science. So there's examples of NASA sending an orbiter to Mars in 1976, and all data is lost. So they come back, and 10 years later, somebody wants to take a look at this, and everything is lost. And if it weren't for somebody who had made printouts of the data, which have been redigitalized, then humanity would have suffered from the loss of this data. And again, I'm talking about standards. There are standard solutions to this, and we should think about them. We should think about these things, and especially how we're operating this long-term data. So, for example, there's the Open Archival Information System, which devises a way and even devises audit protocols to make sure that the things like bit rot and all of these aspects, physical aspects, or how we migrate information over different systems. And we should really think about them immediately before we create our own solutions. So this is probably the message, to really take a good look at what's in other domains. By the way, in my bonus slides, which we don't have time for, I'm not going. These are not my bonus slides yet. It's not there yet. There is an evolving standard actually in the early DIS phases, that is the digital twin framework for manufacturing, where in 4 parts, which are not really yet complete, we could take a quick glance at the underlying principles there. Maybe for those of you interested, we can do this later. I browsed through these documents and looked at what the community is doing, and it might be very interesting to take their lessons and take their approaches to that. Okay, and this is these are the answers to your questions, Yannis, which the slides are shared, I guess.
Yes.
And some of the lessons learned from this are on here. Thank you for your attention.